Welcome everybody. We're here to talk about how to deal with software dependencies. So, who are we? I am Peter Bindels. I've been working at TomTom for the past 8 years, and I've been doing a bit of large code-based maintenance there. Before I joined TomTom, I was working on a library called Hippomox, which some of you may have heard of as well. And while working at TomTom, I figured out that really large code bases are very hard to get an insight into, as in how do they work, how are they laid out, how do we even start with this problem? So in doing that, I figured out it's a good idea to use some tools to figure out how to read the source code, how everything's connected, how things are hooked up. And we wrote a tool. I took a lead and many people in the company followed, and we wrote a tool that does a dependency analysis on a full code base. And I am now the official open source maintainer for that tool at TomTom.
My name is Kiki. I've been working at TomTom for 2.5 years now. I started there as a student. I was working part-time because I was also still studying. After 2 years, I started with my internship there. And currently I'm full-time working for TomTom. During my internship, I had to investigate how we could reuse more components within TomTom. And as a first step, we had to get more insight in dependencies.
Your microphone.
Yeah. So what are we going to talk about today? Well, we will first explain what dependencies are and which types of dependencies can occur. We will then explain what the solid principles are, which are guidelines for writing good code, which also affect dependencies. Well, why do we need dependencies? What are the upsides and downsides? And what are modules? Because some people think that they might solve dependency problems, but is this actually true? How can you reduce dependencies that you don't want? And we want to demonstrate some tools that visualize dependencies in a project. So let's start at the beginning. If we want to tackle dependencies, we first need to understand what they are. And to be honest, it's actually quite simple. A dependency is just a relationship between two components, two classes, two files, in which one uses functionality or types of the other. So, for example, if we have two components, component A and component B, in which A depends on B, then this means that A uses functionalities or types of B. And if this functionality in B is modified, then this might affect A, because A was using that. Also, if we want to reuse component A, we also need to reuse component B, because without component B, A won't work anymore. So what do dependencies look like in code? Well, if we have 3 files, like word.h, string.h, and char-array.h, we can recognize the dependencies as the includes. Everything that I include in my file is a dependency of my file. So, as we can see, word.h includes string.h. So it has a dependency to string.h. String.h includes char-array.h. So it has a dependency to char-array.h. And we can visualize this more simple like this. So as we can see, the includes are now the dependencies. Word.h directly depends on string.h, and string.h directly depends on char-array.h. And these dependencies are direct dependencies because the files directly use the functions or types of the files that they depend on. In this example, there's also an indirect dependency, which is from word.h to char-array.h. Word.h doesn't directly use functionality of char-array, but if char-array.h isn't available, then string.h won't compile, and if string.h doesn't compile, then word.h won't compile either. So if we get a change request for some language support, then we can simply add a header file, which also can have some dependencies. If we then wrap some components around these files, because dependencies can occur at file level as well as component level, then we have, for example, a text editor component, which contains word.h. We have a stringlib component which contains word.h and char-array.h, and we have a language component which contains language.h. If we then look at component level, we can see that we have these dependencies. And we see that language now has a dependency to stringlib, and stringlib has a dependency to language as well. And this is called a cyclic dependency. A cyclic dependency means that both components are dependent on each other. So language uses functionalities and types of stringlib, and stringlib also uses functionalities and types of language. And this is actually something that you want to prevent, because it limits the individual testing of component. If I want to test stringlib, I also need to test language. And if I want to test language, I also need to test stringlib. It also increases the cognitive load and complexity of components, because if I want to understand either stringlib or language, I need to understand the other one as well. So if we remove one of these dependencies, then we will have an acyclic dependency. And an acyclic dependency means it's just a dependency that is not cyclic. So now it's possible to test the components individually. Still need to do that in a certain order. First need to test language, then stringlib, and then text editor. But individually testing is possible. It also decreases the cognitive load and the complexity of the components. Because if I now want to understand language, I don't need to understand stringlib anymore. Components also can have a transitive closure. A transitive closure is a list of all the dependencies that you have. So all your direct and indirect dependencies are in your transitive closure. And your transitive closure tells something about the reachability of your components. So which other components can I reach from my components? If we add a unit test to text editor, then the transitive closure of this unit test will be text editor, stringlib, and language. From the unit test, we can reach all of these components. But if we add the unit test to stringlib, then the transitive closure of this unit test is only stringlib and language, because there's no way to reach text editor anymore. And if we have a unit test of language, then we can only reach language because it hasn't any dependencies to one of the others. If we still had the cyclic dependency to stringlib, then we also would have had a transitive closure to stringlib. So dependencies can occur at different stages in the process of software development. Before compiling, the preprocessor will take the source files and it will preprocess it, and they will preprocess them. And during preprocessing, the preprocessor will replace all the preprocessor directives, like includes or defines, with their values or content. So if you have a header file, or if you have a file that includes a header file, then your include will be replaced by the whole content of that header file during preprocessing. And if this header file also includes a header file, then the content of that header file will be put into your source file as well. After preprocessing, the compiler will check the preprocessed file. It will check if everything that you use in your source file is declared somewhere in that preprocessed file. And if you use functions or types that are declared in another file, you have a compile time dependency to that file. So the compiler only looks at the declaration and it doesn't care about the definition. A compile time dependency can be private. After compilation, the linker will take all the object files which are compiled by the compiler, and it's going to search for all the missing definitions. So it takes main, and it will look for which links am I missing. It will search for these links, and it will couple them to the main. These links can also have some missing links, so it will search for them as well, and it will couple them as well. And it will do this until everything is resolved. During this process, there can be link time dependencies. After compilation and linkage, there can still be some dependencies while running your executable, and these dependencies are called runtime dependencies. So, as I explained, the preprocessor will copy all your dependencies into your source file and your... Oh, this is something that I messed up. And it will take all the... it will take all your direct and indirect dependencies into your source file. The compiler will check if everything is declared, and it will create the object files. Compile time dependencies can be private or public. A private dependency means that an implementation file includes a header file. So, for example, word.cpp includes string.h and word.h. And now the symbols of string are not used in the interface of Word. So I only need string if I want to compile and link Word. And for the users of Word, I only need string at link time. A public compile time dependency means that a header file includes a header file. So now the symbols of string are used in the interface of Word, and I need string for the compilation and linkage of Word, as well as all the components that use Word. So they are needed at compile time as well. So if we have an overview of component A, a dependency tree of component A, which has public and private dependencies. All the public dependencies are the one on the right, and all the private dependencies are the ones on the left. Then we can look at the include path of A, compile time include path of A. So we start at A, and of course we need both public and private dependencies, because a.cpp, or the implementation file of A, includes the header file of C, so we need c.h. It also includes the header file of A, of course, and the header file of A includes B, because it's a public dependency. So we also need B. If we then look at B, there is a public dependency to D. So the header file of B, which was used by A, includes the header file of D. So we need D as well. If we then look at E, we see that there is a private dependency. So the implementation file of B, which isn't used by A, includes E. So we don't use E. For C, it's kind of similar. There's a public dependency to F. So the header file of C includes F. So it's needed for A. C has a private dependency to G, so it's included by the implementation file, which is not used by A, so we don't need G. And then at last we have F, which has a public dependency to H, so we also need H. If we are then going to look at link time, then we can see that we needed all the public dependencies at compile time, but we need everything at link time. And why is this? Well, where the compiler only looked at the declaration of types and functions, the linker will look at the definition as well. So if you have all the object files and there are some missing definition, the linker is going to search for it. For example, if you have word.object, which needs a definition of string, then it's going to search through all the object files until it finds the definition of string. And if it finds this definition of string in string.object, then it will say that you have a link time dependency from word to string. And these object files include everything that is instantiated in your implementation files. So it looks at the implementation files. And if we then go back to our graph, then we have to look at the implementation files. So the implementation files of A needs the implementation of B and the implementation of C. The implementation of B needs the implementation of D and also of E, because the header file of E was first not needed because the implementation file of B was not needed. Now it is needed, so we also need A. And the same applies to G. So we need all the implementation files, and that's why we need all the components. After compilation and linkage, you might think that you've dealt with all the dependencies, but that's not always true. While running your executable, you might still depend on another program or an external interface. So for example, if I have a weather application, which uses a weather API to update its information, then my application won't work without the API. If the API is not available, I cannot update my information, and thus my application won't work. So that means I have a runtime dependency to the weather API.
So we have a definition of solid. Solid is a approach to have reusable object-oriented software. And it comes with 5 prescribed concepts that you need to apply. And of these 5, there are 3 that I will be explaining, which are the single responsibility principle, interface segregation, and dependency inversion. To have a short overview, open-closed basically says that your components should be reusable but not modifiable by others, but it has no effect on dependencies, so I'll skip over this one in more detail. And Liskov substitution principle is a very important part of it, but also has no effect on dependencies. It basically deals with when something could publicly inherit or not. But for more details, look up somewhere else. The ones that do have an effect on dependencies are the single responsibility principle. And we know this from Unix as well, where we have applications and they're meant to do one thing. They don't do anything else. They don't try to encapsulate a whole group of functionality. They just do their own thing. And that means that they only have dependencies that match the thing that they are doing. Which means that if you're using a component that has this responsibility principle applied correctly, you will only get the dependencies that it actually needs to do what you're trying to do. And you will not be getting any indirect dependencies to things that it can do, but you're not really interested in. The second principle is interface segregation. The idea is similar to the single responsibility principle, but it is a fundamentally different idea. The idea here is that your interface represents functions to be used by clients. And your interface should have functions for only one kind of user. If I'm taking as an example a graphical rendering system, then you could think of a 2D graphical rendering system with 3D functions. Maybe we have a bit of Qt in there, we have some other functionality, and we have some sprite movement because some game really like that. This should not be a single interface, because that means that if you're making a 2D game, you will also need OpenGL and other 3D libraries. If you're making a 3D application, you'll need sprite support and font loading, which are the dependencies you're trying to avoid. So in terms of interface segregation for dependencies, you get indirect dependencies for an interface that you're not actually going to be using. The third principle is dependency inversion. And dependency inversion is a very powerful tool. It's basically making things depend on abstractions as interfaces instead of on an implementation. And we don't necessarily care about that for dependencies, but we use it because we can flip a dependency. And in a graphical overview, it looks like this. These are the images from Wikipedia about dependency inversion. And at a high level, that means we have an object using another object. And we would like the arrow not to go in this direction. We'll get into later why we don't want it. But using dependency inversion, we can turn it around into using an interface from object A that it implements. And now object B is using something in A instead of the other way around. So much for high level. So let's have an example. I have a settings file, and it has a few settings. It has volume, it has acceleration, and the volume is notified to the audio system because, of course, my audio system needs to know about the volume. I also have an acceleration, which I need to notify my car subsystem for. This might be a game or automated driving. If I look down there, I have the audio system. And when the volume is changed, it tells the hardware about the volume, which it gets back from the settings. So this leads to a system that if I would like to make an MP3 player with this, I can reuse the audio system, because components, we like to reuse them. We take the audio system, but it requires to have settings. So we include the settings as well. The settings have a dependency towards car, which means that my MP3 player now has to be a self-driving car as well. That's not a good thing. So fixing this would, for example, be making it depend on an interface. So we have a volume listener, and it has the same kind of function that we had before, except this time we're not talking to the audio system directly, we're talking to a volume listener. We have a bit more code to set a volume listener, and we can set the volume and then it notifies the listener, whoever it may be. And the same thing happens with the car and the acceleration. I'm omitting the details because this is already quite a bit of code on one slide. Now our audio system only is a volume listener. It can even be a private inheritance in this case. And it applies to the settings that it would like to be notified of volume changes. And after it's notified, it does the same thing it did before. But if you look at the implementation for the settings, there is no specific other dependency behind this other than itself. Which means that if we reuse settings in a third kind of environment, we don't get the audio system, we don't get the car. And if we reuse audio, we get settings, but we don't need anything else. So why do we have dependencies?
Well, here we always need dependencies to tie our program together. Often our programs contain multiple files, and somehow we need to connect them to each other. And that is where we use dependencies for. Also, they make it possible to reuse components, like other components that I have in our company, or maybe an external library. But dependencies also have some downsides. Everybody wants to keep their build times as short as possible. But as I explained before, during pre-processing, the preprocessor will copy the content of all your direct and indirect dependencies into your source files. Even if you only use one function of this header file, it will still copy the whole content. And this is done for every single source file. So if we have a very small project, a very small source file of just a few lines of code, which has only one or two dependencies, then it's not a really big problem. But what if we have a source file of a few hundred lines of code, which has a few more dependencies? Then during pre-processing, your source file might increase to a file with a few thousand lines of code. And what if these dependencies also have some direct and indirect dependencies? Then your source file might increase to thousands or millions lines of code during pre-processing. And this is only for one source file. But what if you have a project with a few hundred files, and which have a few hundred lines of code, and that all have multiple direct and indirect dependencies? Then imagine that all these files increase to files with a few thousands to millions lines of code during pre-processing. Then it's suddenly not that weird anymore that our build takes multiple hours to complete. Another downside, which is related to build times, is that if I make a modification in a certain file, then all the files that depend on that file need to be recompiled, even if that file doesn't use the modified functionality. In case of a class header, this is even true if I only modify the private members of the class, which are certainly not used by the files that depend on the file. Peter will later explain how you can use pImpl to hide the private members from all the files that depend on you, so that they don't need to be recompiled when you modify the private members. As I shortly explained before, dependencies also have bad influence on testability of your code. So when you have a cyclic dependency, then you cannot test one component without the other. If you remove the dependency, then you still need to test them in a certain order. So first C, then B, and then A. Of course, it is possible to test first B and then C. But if the test then fails, then you are not sure that the failure is in B or that it is in C. And you can solve this with mocking, but that's a total different subject, so I won't tackle that now. And as I said, one of the upsides is that you can reuse components. But dependencies can also have a bad influence on the reusability of your component. Because every component that you depend on, you need to take as well if you reuse a component. So if I have a component that has no dependencies, then it's not really a problem to reuse that component. Also depending on the quality and the size of the component, of course, but we are now focusing on dependencies, and dependency-wise, it's not really a problem. If I have a component with 1 or 2 dependencies, then it's still considerable to reuse that component. Also depending on size and quality, of course. But if I have a component with multiple dependencies, maybe even indirect dependencies, then it's suddenly not that attractive anymore to reuse that component. An exception is when the dependencies also provide useful functionality. So, for example, if you have a component with lots of dependencies, but it does everything that you want to achieve, then it's still good to use it. But what if you have a component with lots of dependencies and it's only a minor functionality that you use? Then you don't want to increase the size and the build times of your project just for that one functionality.
But of course, there is a solution to this. So, who here has heard of modules in C++? That's a reasonable amount. Who here has used modules in C++? That's still 4 or 5. That's actually kind of impressive given the state of implementation right now. So modules started in 2014. There was a proposal done, which was submitted. There was an update done in 2014. There's another update in 2015. There's another update in 2016. And there hasn't been a major update since. It's still revision 4. So that might imply that it's sort of stable and people agree that it's a good implementation, a good design. But actually that might not be true. If you look at the other things about modules, there are pretty scathing ideas. As in, modules may not work at scale, or may work. Modules TS does not support the intended use case. Please to reconsider. Those are not the words that reflect something that's stable and that's going to be in C++20. So why do we have modules? Why do we actually want modules in the first place? It's been in development for a reasonable amount of time, and we have some consensus and implementations, but they don't even agree with each other or with the specification. And the idea is that if you have a module, you would do the same thing as an include, except instead of including the file as text, you're including the file as a binary. It's the definitions that are in there, and they are not affected by the things outside of it. Because that's what's going to happen if you have a normal problem, a normal include. You will have, essentially it includes the text. It doesn't pre-parse it, it doesn't have any idea of what you're trying to say. It just takes the text, put it in there, parses everything all over again every time you include a file. And that basically means that every time you include a file, it depends on everything you've included before it, which people that have used Windows.h may have had some issues with. That also means that if you have such a file, you cannot actually read it unless you know where it's going to be used, which means that there's no way to actually read a header file and know what it means and then write it back out again. So you can sort of prove that it's not possible to make a tool that refactors. So kudos to the guys at JetBrains who do make these kinds of tools, and they work reasonably well, which is really impressive in this state. So the root problem is that we have a textual inclusion. We take the text from a file and put it in the place, And we have macros that can change things as they are being defined. They can add bracket opens without the close. They can add weird definitions. They can change the definition of the things that you have, which means that it's impossible to figure out what's going on. And some includes may affect other includes, as in some files may be incompatible with each other. So we would like to have the ability to say, I have this include file, and it is what it is. There is just this. I am defining some classes, I'm defining some functions, and please do not take any other state into account. Don't use the macros from somebody else. Please stay far away from any kind of namespaces. If somebody else uses extra and C, don't do that. This is what I'm saying it is, it's nothing else. And if you don't have this, you can have ODR violations triggered really easily. You can accidentally redefine something that's different in two inclusions, and then you have a type that's different depending on where you look at it. And most of the software that we're writing actually never does this. Most of the software we're writing actually has simple classes, it has simple templates, complex templates, but it doesn't do any kind of crazy macro tricks. So most of the time we want to tell the compiler, please pretend that all this macro stuff didn't exist, we didn't include it from C and we stopped using it. We're just including a file, we're reusing some other module. So there's a proposal, P0142, which is the current proposal. And it reflects this in literal statements, as in it should be immune to macros. This is the kind of thing that we want. It is not going to eradicate the preprocessor, because some people really like using macros and will keep doing that even if we do this. And we don't want to break their code. We also want to interoperate with it. We want to be able to transition into modules. We don't want to just tell everybody, well, take your code you've written before 2020, throw it all out and just start over. That's not a viable thing for most people. There needs to be a transition. But if you have a world with modules, you should never need to use a header file. You should be able to use module files. So there's the actual implementation of modules, and there's 3 different implementations. There's basically Clang, Visual Studio, and GCC. Starting with Clang, they have the oldest implementation, and it uses a module map to basically tag and include as this include is actually not an include but a module import. And then please read it as a module. And you can also tag other files as this should actually be read as an include statement. Which means that it has very little impact on the actual source code. You can apply it retroactively. But it has a really big downside that this is not what the current proposal is. So if you do this, you'll have to redo it again when the actual proposal gets there. The actual proposal is written by Gabriel de Rooij and Goran Nishanov and other people working on the same proposal. And it uses a module statement to tag something as a module. It uses exports to explicitly say which things you want to export from your module. And you have import statements on the other side to say which things you're trying to import. And that's been in production since 2015. And Visual Studio even allows you to use the standard template library using modules already. They have a proposal out that says how they do it, but they're also shipping it as part of the compiler. And then there's GCC, which does the same thing that Visual Studio does, essentially because it's the thing that is going to be the standard. And they've been working on it since about a year now, and it's been working somewhat since March. But it's far from production ready. But let's look at this through the dependency glasses, because this is the modules as a concept. What does it do for us? Well, looking at it from dependencies, we still have all the dependencies we had before. If it's import something or include something, it's still the same import. You will still get the same code, you will still get the same effects, you still have the same dependencies. If it's public, it still needs to be public. If it was private, it still needs to be private. It doesn't actually fix it for you. Which means that all the things that the compiler did, it still has to do. Except in some cases, it can get around parsing. So with the include statements, you get files that are millions of lines. And that parsing problem is going to be reduced. But most of the template instantiation, most of the actual use, it still needs to do. And taking modules as a separate thing, it doesn't even allow you to get rid of all the template instantiations. You would need to use it with link time optimization to be able to do that. It enables it, but it doesn't get rid of it entirely. And you still have to use it most of the time. In many cases, if you use a template, it does depend on actual types. If you use Fine, it still needs to do all the instantiations to get to the point where you can say whether it's one or the other type, just to understand your own code. Which means that most of the time, it's actually not going to help. So even in a world with modules, we still want to have dependency reduction. We don't want to have dependencies that we don't need, and we want to have the least amount of problematic dependencies that we can have. So how do we reduce dependencies? Well, the first one's simple. If you have a dependency and you're not using it, try to get rid of it. It's a simple question, but it's actually more complicated than it looks. The second thing we can do is convert a public dependency to be private. A public dependency has the downside that it propagates all the includes below it above the, in the tree, which means that all your changes will be amplified and your build times will explode. If you have a code base that is fairly old and has its own standard int implementation, try modifying it and see what your compile times are. A third option is to invert a dependency. In some cases, it's not possible to get rid of a dependency. It still might need to be a public dependency, but we can invert a dependency to avoid cycles. So the first one, if we want to remove a stale dependency. If you're not using a dependency, you're not using an include, then you should be able to remove it. But many people have accidentally added something that indirectly depends on your dependency. People use things that you include, or you indirectly include even, and because of that, if you delete that include, the code base will fall over. In some cases, the code base of somebody else will fall over after you've removed it, and you'll have to put it back in so that they can fix up their code. So as a small example, say we have 3 files. We have a class A in A.h, we have class B in B.h, and class C in C.h. Class A has a member of type C. And oops, I forgot to include the header file, but I did include B. And B doesn't actually do anything, it has nothing, but it does include C for some archaic reason. So if we try to clean this up, and we start on the left side by removing the include, then it falls over, because I have no definition of C. But if I do the other thing, I remove the include from B, then I still have the same problem. It still doesn't compile, I still have no definition. So generally, to solve these kinds of problems, you would start by removing it from a header file that doesn't use it, and propagate that include to the other places where this header file is included. Essentially, you're moving it from your place to everybody who uses it. This doesn't actually increase the total size of your preprocessed files, actually it will decrease it, because if you're including B, you're not including it anymore. If you included A, you already did include it. But people might think that you're adding more includes. And this fixes the problem, obviously, because now we have the definition of C. And now we can also do the second step of removing that last include line. So the big problem there is that we have incomplete header files. There's also a corner case where some people define global variables in header files. And in that case, if you're not including the header file anymore, you will subtly change the behavior of the application. So take this mostly as an encouragement to never put globals in a header file, but also be warned that this might affect you. And in headers, it's a big problem because somebody else will indirectly use code that you are having. In many code bases, you see that there is a bunch of header files, usually 10-ish, that include most of the things that most people want, and most people depend on one of those header files to get them. That's a big nightmare to clean up. But this is at a file level. There's also stale dependencies in build systems. And in build systems, the problem is a little bit more insidious. Because if we have an incomplete dependency tree, that doesn't need to mean that it stops compiling or linking. The library link order changes depending on what things you have and where they're coming from and who's specifying them. But in the end, as long as you have a dependency tree that has all the things that you need, it will compile. If there's 20 things in there that you didn't need, it still compiles. If the dependencies are coming from the wrong place entirely, it still compiles. And that basically means that nobody will fix it until it's so broken that you can almost not fix it anymore. And this has symptoms that you can recognize. And one of those symptoms is that you have include statements with relative paths, as in it couldn't find the include otherwise, so I'll just add a relative include here, go up one directory and go down two. Or just include it from some place, as in the root of all the things that we have, or just an absolute path, just /user/include, etc. Because somebody didn't get a dependency to the component that exposes it. And you will get random build failures when you're removing incorrect dependencies or when you're adding one that should have been there. Because somehow the link order changed and things are now not being found anymore because somebody forgot a link, and that's the reason why it's now in a different order and it's broken. So one thing we can do is take a public dependency and convert it to private. This is a thing that helps a lot on the compile times, but it has limitations. So number one is if we have a public dependency to something else, because it's a template, none of these apply. If you have a template, you must have it at compile time, and you cannot avoid this. If it's not a template, and in some cases if you're using a template, you might get away with forward declaration. If you can't get away with forward declaration, maybe you can use a pImpl, which is a implementation that's externalized, and you might be able to use dependency injection, which is also related. So when can you use a forward declaration? You can use a forward declaration every time you don't need a full type. So what's a full type? You have a full type if you are using the size of the class that you're talking about, if you're using a member of the class that you're talking about, or if you're instantiating a template with that type that does one of these things for you. So not all templates do this. And you don't need a full type if you have a pointer to a type, or a reference to a type, or a const reference, or instantiating the most common templates that you'd be using with it, such as a shared pointer or a vector. If you have a pImpl, that is essentially, you have an interface that describes the functionality that you're trying to expose, and in doing the implementation for that, you would be pulling in a dependency. For example, you have an audio system that links to the audio hardware. In doing that, you expose what the audio hardware classes are, what functions it needs, and what subsystem you're using. All of these things are in your header because in order to define your class, you will be including them, which means that everybody who's using your audio system now needs to know about how you're doing it, which is the separation you didn't want. The solution in that case is to make an interface for the class and to have an opaque pointer to a undefined class, as in you just say that it's a class, you forward declare it, and there's no implementation. And then in the implementation file for this class, you implement the interface and forward all the functions to the actual class that you're implementing it in, and then implement the audio system in that file. That means that all the audio system hardware dependencies are in the implementation file, and you have a private dependency to the implementation and the audio system, and your interface does not expose any of this. It means that essentially you're making it into a private dependency. And the third solution is to use dependency injection. And dependency injection is a term that people have used a lot. And the idea is that instead of depending on an implementation, you depend on an interface. But instead of getting the interface in some magical way, creating it yourself or something, you pass it in. And simplified, that's all dependency injection is. So you get a more componentized code base, you get more reusable components, you have a very explicit use of dependencies, and you don't need any particular library, such as BoostDI, for it to work. You can just pass in the interfaces yourself. It does have the downside that your compile time dependency to some implementation, if there's only one option, now changes to a link time implementation. Which means that many people reading your code now see that you're going to an implementation of X, but you don't necessarily know which one it is. So for some people, it may make it harder to understand your code. And in some cases, we want to invert a dependency. And you invert dependencies when you have a cycle. So you get cycles often. You get cycles when you have a publish-subscribe mechanism, when you have registers and registering callbacks, and somebody calls you back. That's a natural cycle. And for example, if you're implementing code that has a graph that will have to express some kind of cyclic graph, then you will have a cyclic dependency in your implementation. So why do we want to fix a cyclic dependency? Well, if you depend on one thing in a cyclic dependency, then you will depend on all the things in the cyclic dependency and their dependencies, and any cycles correlated to that, and anything below that. So for an example, I'm writing a simple program. It's really simple. It just displays a graphical window, it plays a movie. So I need my movie library. And the movie library has a graphical interface and a few other dependencies, so I'll need those as well. But somebody implemented a movie library with some kind of weird mechanism that causes cyclic dependency. So I get a bunch of other components that I sort of need, but I don't need all of them. But I get them anyway. And I'll get some dependencies for those. Because, of course, they need things to implement it as well. And one of those things that I don't necessarily need has a cyclic dependency, which pulls in all its dependencies. So if you're including all of these things, you might as well include all the things. But if you're going to include all the things, why do we bother with components anyway? Just make an all the things component. Just include that, you're fine. So why don't we?
We do. It's called precompiled header files.
We try not to. But that is actually related to modules.
Modules are just that implementation.
Mostly, yes. That's why Visual Studio has such quick implementation for it.
Yeah.
So the root cause is that in doing so, you actually make everybody depend on everything. So if you're making a simple Hello World program, you will be getting a translation unit, you will be getting internationalization support, you will be getting datetime libraries. You have a dependency on OpenGL all of a sudden for saying Hello World. When actually, if I look at my program, I'm using this. I'm not even using all the dependencies of A, but most of the things I'm never touching. I don't need this. And if I could just take the things that I want, I would get this, which is a simple program. You can read this, you can understand it. It's not that hard. And the second thing is that if you're testing a single unit, but because of all the dependencies that are tied to it, it's impossible to test any of the components in a cycle without including all the other things in a cycle. Which means that you get an executable that looks more like this. I've seen a unit test for a single function be 100 megabytes. Essentially because of this. So what are the reasons we want to fix cyclic dependencies? So we want to remove them to avoid having a fake indirect dependency. We want to remove them to reduce the size of the build tree that we're passing in, so we have a shorter command line, don't have command line accesses, as in there's a limit to it, and maybe your build system can't pass it into your shell anymore. We want to have less change impact. When I'm changing a single file, I would like it to be a fast rebuild instead of 3 hours. I want to have it testable, so that I can change something and expect that it works without including 25 threads started by somebody who I don't even know, who accidentally has a memory corruption after 3 minutes, and because my test is long enough, my test is now crashing because of his bug. I want to avoid link order instability. If you have cyclic dependency, your linker actually needs to list all the libraries infinitely many times to be sure that it links. It's practically impossible to do that, so they list them some number of times. CMake by default does it twice, and then says, yeah, it's good enough. And you can tell it how many times to repeat it, but there's no number that will ever be good enough for everything. If you don't have a cyclic dependency, you don't have this instability. You can't have it. So you avoid link failures. Make it more comprehensible, because now if I'm looking at one component, I know what's going on. There's 3 threads running, I started them. I don't have the 25 from somebody else. I have a more stable system, because when I'm linking in just one component, I get that one component. I don't get all the other things running on. My unit tests are a lot faster because they don't start all the stuff that I'm not trying to use. And there are so many reasons. And there's even a bigger one, because, you know, just to show, when you park your car, you're basically expecting people wouldn't break into your car. And you do that because your car is in a good state, it's maintained, and people see that it's being used. So if you park your car in a good area, you sort of can expect that to happen. If you park it in a bad area, it will actually not be broken into until you break a single window or make a single scratch on the car. And then in the right areas, your car will be stripped in a day. And the idea behind this is essentially the moment that people see that something isn't entirely maintained or isn't entirely right, they don't see that they're adding a lot of problems to it. They're not making it much worse. They're just adding one dependency. What's one dependency? And that means that if you have a build system with a few problems, if you have a few examples of this is not quite the way to do it, then people will copy that. People will imitate that. People will use that kind of implementation and make it worse. So we want to get rid of cyclic dependencies. How? So let's start with an example. We have a cyclic dependency between A and B. I'm just using generic A and B as in it's a thing. The first thing we can do is find out that actually one of those components has a file that should have been in the other one, but for some reason somebody put it there. So we just take it out and move it to the other side. This helps a lot, and this is a very common thing. This happens because we have unclear componentization. Somebody made a component and gave it a name, but didn't quite specify what should and shouldn't be in there. And just moving the file will fix it. This is the most common thing you can do, and in most code bases, this fixes about half the problems you have. Just take the file from the wrong place, put it in the right place. The second biggest problem is having components that do more than one thing. So the basics, single responsibility violation. And then you can split it into two components that do two independent things. Now one is going to B, and the second one is going to the second half of A, which has no link with the other half of A. But of course, usually, there's more things in A. And you typically recognize these things by their name, because these are the engines, the system, component, frameworks, support, whatever the name is. Most of these things have this problem because there is no definition what should be in there. It's just a gathering basket of all the functions and classes that somebody made and somebody had to put somewhere. This is very, very common. And the best solution for this is just to take one responsibility at a time, take it off, and put it in a separate component. And keep doing that until you actually realize that now this thing called engine system util actually has one responsibility that I can give a proper name. Now it's called settings, and not all the other things. The third one is inverting a dependency. This one isn't quite as common, but it's pretty high up because this is the one that you're probably going to have to do. This happens if you have a cyclic dependency that's sort of native. You have settings and somebody changes a setting, it propagates back to other people. You have a configuration, you have some startup logic, you have classes that call into each other. You have a native cycle. And this is the biggest thing you can do to get rid of your cycles. Most of the time, if you have one cyclic dependency of this type, that cyclic dependency will also represent 20 other cyclic dependencies to the same component. As in, if I'm doing settings wrong in one place, I'm doing it wrong in 27 places. Fixing that one place is a really big code change because you're adding an interface, you're changing the code, you're making a callback, you're making a registration, you're making unregistration, you're changing lifetimes, and then you're doing that to 26 other components. It's a really big code change and people will fight back, but it's the best thing you can do to fix your code base. And then the less common solutions are to essentially extract a component. There is something that's shared between these two and they're talking to each other because there's some hidden component between them, but otherwise they don't talk to each other. So take out the component, take it out, and put it back down. This happens because people write software and add functionality over time. There's some form of organic code growth. You add functionality and some people just don't do the refactoring that should have been done. At some point, you're just going to have to go and fix these things. Just start finding out which component is it, what kind of responsibility did we spread across two components, take that responsibility out, give it a proper name, and make it into a different component. You just put two responsibilities into, three responsibilities into two components. And this is fairly fixable. The second one that happens is having a driver. Essentially, there's an interface above the things that we were doing, and this interface wasn't represented as a component. We just sort of left it in there. Again, this is organic code growth. This happens when you're writing software, when you're doing deadline releases. People will make these kinds of mistakes. And the idea is to just take the API, move it up into a different component. And in this case, it's an interface segregation violation because you had an interface that's on A that actually is 1.5 interface. But it sort of looks like segregation violation as well. And then the last option that you have is to concede. As in, we have A and B, and for some reason people thought that this was two separate things. And we tried to keep them separate, but there's no viable way that I can make this into two components. The best thing you can do is just make it one. Just be honest about the thing that your code base is. If you have a code base with a lot of cycles, this would mean just making it into the big blob otherwise. But at least now you're honest. You're actually saying, I have a big blob and I need to fix that. So it's the least useful thing you can do. It's essentially the same thing you had before. The only thing you change is that you're now saying, well, I have this big blob component that I need to fix. So what you're probably doing is taking everything together and merging it into a giant single responsibility violation and interface segregation violation. So the best thing you can do then is find out if there's a responsibility I can split out again and try to clean it up.
So we now know what dependencies are, when they can occur, and we know how to reduce them. But if we have an existing project and we want to reduce our dependencies, we don't want to go through all the files in order to find our unnecessary or wrong dependencies. We rather have a tool that gives us an overview of all the components and the dependencies between these components. Peter and I have both worked on such tools. Peter has created Cpp-dependencies, which scans a project and creates an overview. And I've extended that tool, and I created the tool Spindel, which uses the Cpp-dependencies with a more interactive UI. So Cpp-dependencies analyzes a project, it takes all the source files, it goes through the files and looks for includes, and it searches for all the compile time dependencies. It also shows the cyclic dependencies, which you most probably want to remove. And Cpp-dependencies is mainly a command line tool. So yeah, you use it, for example, to get a path from one component to another component. So you say, like, how do I go from A to B, from A to D, and it will show you the path. You can also request all the ingoing and outgoing dependencies of a certain component. You can see how much lines of code are in a certain component. You can even generate a CMake file automatically if you want. So there are a lot of things that are possible. You can also, it will also generate a dot file, which can be used by a graph library like Graphis, and this will create a visualized overview. But this overview is not very interactive, and it's, for big projects, kind of a chaos. And at last, Cpp-dependencies is not really newbie friendly. If you want to use it, you really need to know how to use it. If you just want to check something very quickly and it's just your first time, then yeah, it can be hard. So the output of a bigger project can look like this. And there are quite much components and lots of dependencies between them. And if we zoom into this, then we can see that there are lots of lines, but I cannot really see where they point to, because they mix up. And that's why I started to work on Spindel. Spindel is an interactive visualization of dependencies within a project. It contains also all the public and private compile time dependencies, but it has an interactive overview. It is a combination of Cpp-dependencies for scanning the project and finding all the components and dependencies. And I've used Dia Diagram Editor for the functionality of an interactive UI. So at the base, we have Cpp-dependencies, and it gives me information about the components and all the dependencies. And I will store this information into models. The Dia adaptation then uses this model to build up a dependency tree, which can be visualized in Dia. And I've also added some features later, which I will explain in a minute. So the output of Spindel looks like this if we are completely zoomed out. So it's a big project, there are still lots of components. But if we zoom in, it looks like this. So there are still a lot of dependencies that go through each other. And depending on your project, the components can be closer to each other, and there may be more lines interfering. But I've added some features for this. So I first started with a feature to highlight a certain component and its dependencies. So as a user, you select one or multiple components, and Spindel will highlight these. So you can see where the line is actually going to. The second feature is that you can select multiple components in which you are interested, and you will display it in a separate overview. So you have a smaller overview with only the components you want to see. And at last, I made a folder structure overview so that it's recognizable for the developer, because mainly you're working with the folder structure while developing your code. And this way you can see like, these are my folders, and these are the components that are in the folders. And also if you have like third-party code, which you are not interested in what the dependencies are, then you can close this folder and you won't see those dependencies. And we will now give a demonstration of Spindel. Waar heb je die staan? Waar staat die bij jou? Ik weet niet waar je die voor hebt staan. Dat je de balkon niet was. So if we look at our project, well, we zoom out, and we go to a piece with a lot of components. Then we see some lines. And if I then select the highlighter button, then I can select any component that I want. And I can see where my dependencies are going to, because they are highlighted now. And I can also select multiple components if I want. And when I do this, these components will also be put in a separate overview. So here I only have the components that I selected. And I don't have all the overhead of the other components that I don't want to see. We can also go to another diagram in which we see all the folders that we have. And it's still work in progress, so it will first zoom out, and then that's something that needs to be fixed. But if I zoom in again, I can see that I now have a component here, which has dependencies in this folder. And this way you can show all the dependencies, but you can also hide the components in the folders that you don't want to see. Yeah.
So this essentially is the same overview that you just had with the entire graph of everything, except this time you're able to see what's going on, and you have some insight into the actual components you care about. And all the other ones, especially the ones in the include folder, for example, we're seeing that now as one big component, which makes it much more insightful. We also have a small demonstration of Cpp-dependencies itself. Let's see if I can set this to a presentation. Yep, that's better. So we can analyze the project that we have here. It's a small project that we've created for demonstrating what the problems can be that you see. So in this case, the problem will not be very hard to find because there's not a whole system around it. But we do have a problem because we have 3 nodes that are in a cycle. We have 7 components in total. And we have a few dependencies between them, but not that many. So the first thing we can do is ask it for a graph of the things that we have. And this is exactly why we need Spindel, because there's a few things that are not quite newbie friendly. So the first thing we have is that we can generate a dot file, but we can't actually see that dot file. We can look at it in a text editor. And it will tell you everything. In this case, it's sort of understandable, but it doesn't really tell you anything. It just shows the links. In a big project, this file will be thousands or 100,000 lines long, and it will be very impossible to look through it and find the things you want to know. So the things we want to do is pass this all into a tool, such as dot, which is able to render this into a graphical format. And then you can view that in any kind of graphical viewer. Which will show you that it's a project. There are some dependencies, and this already tells us a lot. If I'm looking at this overview of all the components that we have, what do you see? Can you name a thing that you're noticing? You see a cycle. Well, I see two. So I see a cycle between util and graphics. And I also see a cycle from graphics through view and util back to itself. Which means that we have components that are not separately usable. We cannot use anything from util without using graphics as well. And we cannot use graphics without using view as well. There's a second thing that I'm noticing. You can assume that the exe is the executable that we're going to create from this. It's the final build step. Well, build is unused, which is my build folder. That is correct. Is there something else you're noticing that is unused?
Settings.
Yes. So there's nobody using settings. So why do we have that? Maybe that's just a library that we had in the past. Nobody's used it. But we should be able to get rid of it. So let's see if we can do that. So let's just bluntly remove settings. Boom. And now let's just build again. We're not updating build files, we're just building. Sure, why not? Because I'm actually regenerating all the CMake files every time. I didn't write any CMake files. I just told it, well, just go and make one that sort of represents the thing that we have here. I don't need to tell it what's in there. I can go into a different project. And it does all the things in a CMake file that you would expect from simple component analysis. It doesn't do anything clever. It doesn't go in onto GitHub to download catch. It doesn't do anything in terms of compile options. If you do that, you will need to specify them directly. And it doesn't go outside of your project to go and look at in some kind of system library to find if maybe that's the thing you're using. But for many projects, especially big projects that have most of the code linked to each other, this is a thing that can save you a lot of time. Especially because I can't make a mistake in all the dependencies because I don't make any dependencies, I never write them. And we can see that there's a link to graphics from assert. So what could we possibly be doing in assert with graphics? Let's find out. Ah. Yeah, of course. We're printing asserts in red. Because we like to have red colored asserts. And we're getting a NZ sequence with that, which is to do. But actually, why are we using color, which is a graphics concept, in a util library? That seems to be a dependency in the wrong direction. Or is it? So we can remove color here. Or we can decide that actually color should have been here, but was put somewhere else. As in, we thought it was a graphics concept, color. But actually, it's a utility class that doesn't do anything graphically. So suppose that we do that. We go to graphics, and we move all the color files into the util folder. And we rebuild, which works, of course. So what do we do to the dependencies now? So let's see what it's looking like right now. And now this looks like a more sane thing. Or is it? Because we did fix the cyclic dependencies. We can see that with the color of the arrows. We did remove settings because nobody uses it. But now we're seeing that nobody's using graphics. So the only reason we had graphics was for color, and there's something else in there, otherwise it would have disappeared. But there's now something in there that nobody uses, so we can get rid of that. And in the end, this basically allows you to take a project and without necessarily going very deep into all the subject matter, still be able to understand it, understand the dependencies, and find out why things are there. So one final thing that I can demo, which is why there is a link from graphics to util. Sorry for the typing speed. It's kind of hard with just one hand. So we have a link from graphics to util, but we don't have a direct link. We have only an indirect link. So we have graphics, which is using view because the viewport includes window. And we have a link from view to util because window uses a search. So that's nice. Now we know. You can also ask for links that don't exist. For example, is there a link from graphics to the executable? And says, nah, there's nothing. You can use this in a build system to automatically find whether some links exist and assert that they don't. As in, you can use this to prevent problems from arising in your system just by checking ahead of time that you weren't introducing them. Okay, let's not start from the start again. That might be taking a bit long. So we have a few references. We have the slides, which are going to be on that link very, very soon. I have the Git push standing ready. The link is right there. So if you can't have a QR scanner, you can also use the link. You can find Kiki on LinkedIn. You can also find me on LinkedIn, but I forgot to put it there. I'm also on Twitter. So feel free to reach out at any point. We have the dependency checker on the TomTom International GitHub, which is the official one. So feel free to contribute or ask any questions about it. Do you have any questions?
Share that microphone. Take it off, and then just share that.
Oh, take it off.
And nice presentation, thank you. I have a first question about your tool. I'm wondering, because it wasn't shown, how do you find the include paths and all that stuff? Do you like to take the compiles commands from CMake, or?
Actually, we're not actually doing anything with the CMake files themselves. As you saw, they are completely regeneratable. We don't use that as an input other than to know if it should be an executable or a library. We've recently found out that actually you can derive that as well. So we shouldn't need it at all other than to find out where your components are, so we don't map your include file to include path to a different component than your source file.
Yeah, that was my point. How do you get the path to the include to make sure that you can actually find an include if you don't have the build system information?
Well, that's a really good question, because in some cases you might not be able to find that. As in, there are two files with the same name. There's an include path, there's an include statement that could map to either one. How do you then know what to go to?
Well, you get the -i from the compile commands, for example.
And if somebody changes dependencies, then all of a sudden your build starts failing because you have an ambiguous include and now it's using something else.
Yeah.
Which might be somebody else's dependency again. So if you have a link between component A and component D, and you're adding now a link between component B and C, then all of a sudden that include falls over.
Yes, but usually you don't do that. I mean, like you put a prefix or a namespace or something, like a header hierarchy, so that you make sure that there's no like util.hpp that comes up like 10 times depending on the include path.
You would be surprised how often this goes wrong.
Yeah, I guess we have all cross to bear. Which brings me to my next question: how big can you handle a code line?
How big the projects can be?
Let's say, for example, 1 million line, a couple hundred of libraries, probably half of them in the cyclic dependencies.
We've tried it on a 7 million line project, and we basically do that in 2 seconds.
Not bad.
Does that answer the question?
Yeah, besides the include path problem, but yes.
Okay, let me see if I can demo the include path problem. That may have been a bit fast. So I can basically tell you all the includes that you have that are ambiguous, why they're ambiguous, and which things are trying to do such an include, which is ambiguous, and what they're going to. So in this project, I have a whole bunch of files that are including std.afx, which is a Windows system for precompiled headers. And all of them are just doing include some std.afx. And all of the ones listed here don't have a std.afx in their local folder. So all of these could find any one of them, which could be common or some include path, and all of those could be failing at any point.
You have a strange way to use -I, I would say, from here. We can talk about this afterwards, because I don't know, there's something I don't get, obviously, here. Which brings me to my second remark, which has no bearing to that. It's just like you said, the problem with people who use includes, well, you use stuff but don't include them. My take on that is that those are bad people and they should be shot. No, if you use something, include it. Because other than that, it's very hard to tell if you are actually declaring the right dependencies or not.
Well, yes. So basically your includes should be reflecting the things you're depending on exactly.
Yeah.
That's the basis of this tool, as in I'm assuming that your includes are perfect. And your build system is terrible. And we'll use the includes to make a build system. And then the build system finds the right includes.
That's an interesting way of...
It feels backwards, but it works.
Yeah. Well, I actually have a talk in like 10 minutes whether how to use CMake and go from the build system to the code architecture and not the other way around. You're welcome.
You can relax a little bit because you still have half an hour.
Sure.
So that's good news. I'm very interested in that, and I would recommend people to see Mathieu's talk as well. If you look at the terms that we've used, we've intentionally chosen them to be the same thing that CMake does. So if we're saying we have a public dependency, that maps directly to CMake being a public target link library. If we have an include path that's public, that maps directly. So if I go back to the project that we have, which is, if I look at any of the include paths, this one will not expose any include directories because nobody is trying to include it. So it doesn't need to expose anything. It has a private link to Vue because it's using something from Vue, but nobody's depending on that. Nobody's including that file indirectly. And if I go to Vue, second. This one will have a bit more information because this one has a public include directory because somebody's including window. Window is including util because it's a public dependency and we can see that in the code. And when compiling this, we'll need util. And when linking this, we will need also to have util. You can see that information in a graphical form in the overview that's generated. We've used the same colors in both Spindel and in Cpp-dependencies. So if you have a private link, then that is a light blue arrow. If you have a public link, it's a dark blue arrow. And if you have a cyclic link, then we'll just make everything orange because it's terrible. So in this case, we know that the executable uses Vue privately, as in it doesn't expose it because nobody includes anything from an executable. Graphics doesn't expose anything because nobody's using it. And Vue is exposing util because somebody implemented something in a header file and shouldn't have. Next question.
Just out of interest, did you ever use the tool include what you use from
Yes.
Clang? Just out of interest, what's your experience with it?
Has anybody else here used include what you use? There's a few hands, but not enough. Basically, this tool will use the include files to figure out what things you're using, assuming that your includes are correct. Include what you use is doing the opposite. It assumes that your includes are completely terrible, and will find out which things you should have included and which things you don't need to include. And it's a complementary tool to this one. It's essentially those two in combination will allow you to clean up your includes and then clean up the build system, and by cleaning up the build system, clean up your includes more. I strongly recommend it.
More questions? All right, that looks good.
Okay, thank you for being here.